want to get further conclusions. So if there's a point, right? So this is like an initial condition. So at this time, this is the point the curve will pass, right? So that's this is just like this. Instead of using T0 as S, right? And this S, the value will be C, right? Yeah. So if that's the initial point, then there exists an interval. Here's a notation associated with the point. So it is an interval associated with this initial condition. Right, so there is an interval such that on this interval a solution of the initial value problem exists, and also it is unique. And it is the largest possible interval, because if you have another solution satisfying the initial value problem on a certain interval, that interval must be a subset of this interval. So
is this guy in B?
we want to show for an initial condition there exists an interval. Let's write this statement. Okay, complete statement. This interval certainly containing the S, right? Containing the point as this, but this time, this is a time interval, right? Because some solution is from this time interval to Rn. Yeah. So containing S and a curve. The curve, of course, from this interval to Rn, satisfying the initial value problem. Satisfying, so that's the initial value problem, which is this vector field T, X, and this is the initial condition. We use a slightly different notation. Yeah, so we want to further conclude that this interval is the largest possible interval where there's a unique solution. That means if there is another solution, so furthermore, if beta, okay, so beta is another curve also satisfying the initial value problem. Then this interval must be a subset of that interval. So the J must be a subset of this interval. Yeah, so that is the theorem, yeah, primary theorem for this section. So I want to ask you whether condition conclusion is clear to you. So if you have any question, we can try to understand the notations first, the meaning. Yeah, okay. Okay, so actually we can try to prove it, because when you prove it, everything will become more clear. Yeah, so so next we can think, how do we construct such an interval? It's larger than yeah, it's at least a superset of other intervals where there's a solution. Yeah, the largest possible interval. So the proof is actually a proof by construction. If we can find an interval such that we can define a solution for this problem, then we found a solution, right? Yeah. So in the proof, actually, we want to construct this interval. That's the time interval. Okay, so before we do anything, can we think of, just think, spend one moment on the construction. Yeah. So we want to, for this problem first, how many possible intervals do we have for that system with the initial conditions, with the differential equation? Yeah, for the system. How many possible intervals? So let's say if I have a curve, I know according to the assumption, right? Given for the given system, we have a unique solution. Right? The unique solution is beta, right? Yeah. So it's this, right? The Rn. This is from the time interval to Rn.
Right.
Yeah, so we know there is solution for some interval, right? For some interval. Okay, this interval you can just write this, right? Some time interval from A to B. This is from time interval to Rn. So yeah, for some interval, on some interval we have a unique solution. Maybe the interval, but AB can be different, right? There is another interval. So this A can change, right? And B can be a different value. Then on another interval, the solution still exists, but the common thing is S has to be in the interval. Yeah. So that's the common thing. So it's an interval containing S.
So you want to find the biggest so that it
Yeah.
still contains S.
Yes. Yeah.
So then we have to have a bound on S. I mean, not a
Yeah, we must have an interval that's so each one of those intervals is a subset of that interval. Right?
But
Yeah.
then it still has to contain S.
Yes, the larger interval has to contain S. So how do we construct that larger interval? We know, according to the existing uniqueness theorem, we know there is at least one interval, right? On this interval, there is a unique solution. No problem, because we have the hypothesis, which is the same as the before. Yeah, so yeah, maybe for another interval we still have this, but we know we can find a small enough interval they are unique, right? We have uniqueness. But now how can we make it as large as possible? Yeah, among all these intervals, there's a left end point, right? For all the intervals where there is a solution, unique solution, for all this, there is a left point. So we can put all the left points in one side. So I will use the notation as same as the book, so you can understand it later as you review the proof. This L is the set of all left points on the interval where there's a solution. Yeah. But also we may have many intervals on which there is a unique solution, right? So on all of those intervals, we put all the right points in a set. So here is the notation. That's the set of all the right points. Yeah. So I just briefly go over the notations, then we can put the left point and right point in two different sides. Then we want to make the left point as small as possible, right? Yeah, so what do? We take the lower bound, right? Lower bound of all the A, right? All the A's.
Right bound.
Lower bound, but you cannot make it too low. Lower bound can be smaller, much smaller than all the A's, sure. But we want to find the infimium of all the, yeah, so we just pick A. A is that, right? But for this set, we take the infimium. That is the greatest lower bound. Greatest lower bound. So we will find a value. And then next, we will, for this one, because it's a collection of all the right points, right? So for all those B, we will find upper bound. Upper bound. Then what is the upper bound? We want to find the least upper bound. Supremum of all the B's. Yes, so the least upper bound. Left, right. So let's use R. So that number, L, the infimium of all left endpoints. The supremum of all the B's, then we'll give an interval, which is the largest possible interval. We can have a unique solution. So that's the idea. That's the idea. So we just see this, then let's construct this interval. Then once we have this interval, we will further check whether there is a value, right, for any t on this interval. So here we can find an interval. Then later we will see what if I pick any t in this interval. Do I have a value? Do I have a, because we want to make sure on this interval, right, whatever interval, you identify the largest possible interval. So, but I want to make sure for any t on that interval, I have a value, right? Yeah. So later we will further justify the value, the beta t. Yeah, we do have a value for any t on this interval. And it should be clearly defined. And the value is unique, right? We want to further justify all that. So once that's done, that's the proof. Yeah, so the main thing is to show this is true, we just use the construction method. We construct the largest possible interval first. So consider all the intervals, right, based on that, and then we can construct the largest possible interval. Then after we have constructed the largest possible interval, next we will show for whatever t from this interval, there is a value. So the solution is defined, clearly defined as a unique value. So that's our approach. So and still the notations will be the same as the notation in the book. So when you review, you can